I'm going to share the screen for Canvas web page. Can you see my Canvas web page now?
Yeah.
Okay. There are some people who haven't taken the test to last Friday. I'm reopening the test too for those who haven't taken. So check your email if you haven't taken the test yet. So please complete quiz 3 and quiz 4 and test 2 in module 2. Then you can start on module 3, chapters 5 and 6, and test 3. We may not have enough time to cover chapter 7 and 8. I'm going to put the resources on the Canvas web page. You can go it yourself, and let's see how it works out after we take the test 3 on chapter 5 and 6. Finals going to be on chapters 1 through 6 that we're going to cover before end of quarter, chapter 1 through 6 for the finals. So you go to the module 3 to access the material for module 3 is here. The chapter 5 is on gases, liquid, and solids. So we're going to go over some of the topics we already covered, 3 states of matter, and do more detail about these 3 states: gaseous state, liquid state, and solid state. We're going to look into most of the concepts dealing with gases, liquid, and solids. Chapter 6 is going to be on solutions and colloids, chapter 6. It's mainly water solutions. We're going to look into that after we cover chapter 5. Do you have any questions about anything? One question I keep getting in the email is, when you do look into Zoom meeting, I give 10 points per Zoom meeting. Then people are asking me why I did get total 10 points for the grade. Attendance is only 10% of attendance grade. Therefore, if you get 10 points, total grade contribution to the total grade from the attendance is 1 point. Therefore, don't expect total 10 points for each time we do. Attendance cannot exceed more than 10% of the grade. Okay? Whatever the grade shown in your grade book is correct. You get 1 point for watching Zoom meetings. All right. I'm going to go to chapter 5 and start from there. Can you see my chapter 5 slide page? It says chapter 5, gases, liquid, and solids. Can you see it?
Yes, sir.
Okay. We're going to go chapter 5 now. Chapter 5 deals with details of gases, liquid, and solids. Basically, the three states of matter in detail. We're going to talk more about states of matter. Then we're going to look into gaseous state, starting with measurement of pressure of a gas, how you measure gas pressures. And we're going to talk about behavior of gases, how gases behave. Gases have pressure, volume, temperature, and amount of gas expressed in moles, number of moles of gas. So when we change one of these variables, volume, and how that volume change affect pressure, temperature, and number of moles are the behaviors that gases show when you change these four variables. There are gas laws describing these behaviors. One of the gas laws is called Boyle's law. Other one is Charles' law. Third one is Gay-Lussac's law. Fourth one is Avogadro's law. So after we done all gas laws, including ideal gas law and Dalton's law of partial pressure, we cover a lot of details about gaseous state. Dalton's law of partial pressure describes the total pressure of a gaseous mixture, like atmospheric mixture of gases in the atmosphere. Atmosphere is made out of nitrogen and oxygen mainly. So partial pressure of oxygen, that's pressure exerted by oxygen, and partial pressure of nitrogen are added to, according to Dalton's law of partial pressure. So those two, each pressure exerted by the certain gas in the mixture is added up. Sum of the partial pressures give the total pressure. We also go into little more detail about molecular theory, kinetic molecular theory, to describe gaseous state mainly, and then look at how the kinetic molecular theory applies to liquids and solids. One of the most important things we learn in this chapter is intermolecular attractive forces. These are forces that act between particles in each state of matter that creates certain state to particular compound. For example, water is a liquid. Why water is a liquid? Because water has higher intermolecular forces. Methane is a gas. Methane has lower intermolecular forces. We're going to talk about three main types of intermolecular forces. We're going to describe them. Once we know the intermolecular forces, kinetic molecular theory, we can describe behavior of gases as well as liquid at the molecular level. Also, behavior of solids at the molecular level. So we're going to do these topics in detail. I'm not going to go over each topic in the instructional objective right now. We will come back and look at once we finish the details of each topic. So there are 12 topics that we're going to talk about. The first topic in chapter 5 is states of matter. This is something that you already gone over. Solid is one of the states of matter. Liquid is another state. Gaseous state is the state with particles far away from each other. Liquids and solid and liquid states are called condensed states. Condensed means they are close to each other. So we can look at the details. A solid has definite volume as well as liquid has a definite volume. The volume of a solid is depend on the volume, shape of the solid. It doesn't depend on the shape of the container. But even though liquid has a definite volume, the volume take up the shape of the container. In gases, there's no definite volume. It depends on the volume of the container. It expands into the shape of the container. Therefore, volume is not definite for gases. We talked about these things. Solid maintain the shape regardless of the container. Liquid takes up the shape of the container but has a definite volume. Gases have no definite volume and it assumes the volume of the container. Solid particles are close to each other. They don't move. They only can show vibration as the temperatures increase. Liquid, on the other hand, can move or slide over each other. Therefore, it flows, take up the space of the container. Gases also moves in every direction randomly. Therefore, take up the space of the container. Gases only have pressure on the wall of the container. Liquids have a pressure if it's pumped. If you use a pump on a liquid, you have a pressure. If you don't use a pump to force the liquid, there's no pressure in the liquid. There's no pressure exerted by the solid. Therefore, pressure is exerted only by the gaseous state. Let's look at some problems. Which state of matter has the weakest attractive forces between its molecules? There are attractive forces between particles in solids and liquid phase. Gaseous phase, there's no attraction. Therefore, weakest attraction is in the gaseous phase. A gas has weakest attractive force between its molecules. See the correct answer. Attractive forces are strongest in solid, then in liquids, then in weakest in the gases. Which of the following leads to increase in kinetic energy of a molecule? Kinetic energy is associated with velocity. Kinetic energy, we talked about it, half mv squared. M is mass, v is velocity. Therefore, kinetic energy is related to velocity of the molecules. Therefore, velocity in molecules is related to temperature. As you increase the temperature of a gas, the particle of the gas moves faster. Therefore, kinetic energy is directly proportional to temperature of the gas. Which of the following increase the kinetic energy of a molecule? Is the temperature. An increase in temperature. Intermolecular forces doesn't increase with kinetic energy. No increase density or increased surface area. Kinetic energy is increased by increase in temperature of gaseous in the molecules, particles on states of matter. Which physical state of matter is represented by the following model? If you look at this picture, it's certainly not a gas. It's between liquid and solid. Liquids have a particular shape on their own, but here that particles are taking up the shape of the container. Therefore, it should be a liquid state. Answer is B. Let's look at more problems. When the state of a substance changes from A to B, as represented in the diagram, which of the following statement is true? Velocity of the molecule increases going from A to B. That's false, because gaseous state has more velocity than the solid state. B is the solid state, gas to solid. Velocity doesn't increase. Velocity decrease, or velocity motion of the molecule is more restricted in the solid. The strength of the intermolecular force increase. That's the correct answer. As a gas goes to a solid, as kinetic energy is slowed down, intermolecular forces can take over, and therefore intermolecular forces increase. The kinetic energy of a molecule decrease. Going from A to B, that is a true statement. The strength of intermolecular forces increase, and the kinetic energy of molecular. The correct answer is both B and C. Intermolecular forces increase, and force of the kinetic energy of the molecule decrease. Number 4. Temperature of a substance is decreased by to a low value. Which of the following would represent the substance at the lowest temperature? There are 3 substances, A, B, C. One is, A is liquid, B is solid, C is gas right here. Which of the model will represent the lowest temperature? Lowest temperature is solid, which is the B. So answer is B. Now we go on to describe pressure of a gas. What is the pressure of a gas? Pressure of a gas is due to collisions of particles, moving particles of gas, hitting the walls of the surface. It is the force per unit area exerted by collision of the particles. Surface is the wall of the container. Most commonly used pressure unit is millimeter mercury and also torr and ATM. ATM is called atmospheric pressure. There are three common units used for measuring pressure: millimeter mercury, torr, and ATM. You have to know conversion factors for these three units. One atmospheric pressure is normally the average atomic atmospheric pressure of the air in the atmosphere. One atmosphere ATM is equal to 760 millimeter torr. This is the height of a mercury column that I am going to show you in the next slide. Atmospheric pressure is measured in millimeters mercury. Millimeter mercury is also another name for torr. Millimeter mercury is same as torr. There's a fourth unit for pressure called Pascal. That is the SI unit. Then sometimes we use mercury, inches of mercury, and also a unit called bars. So all these conversion factors will be given to you. One atmospheric is 760 millimeter mercury, 762, one atmosphere is 101, 325 pascals, inches of mercury 29.92, and one atmospheric is 1.01325 bars. Conversion factors you already use using the factor label method to convert one pressure unit to another. How do you get 760 millimeter mercury for one atmosphere? Let's look at how you get 760 millimeter mercury. Gas pressure is measured using initially use a mercury barometer. Mercury barometer is a column, a tube, closed-end tube filled with mercury. If you put the mercury column into the mercury beaker, this column always had the 760 millimeter mercury. This height is 760. That is the weight of the air that is acting upon the mercury surface here. This weight of the air is that. That means, like in underwater, if you are in the atmosphere, we were acted upon by all the air on top of the atmosphere. That weight of the atmosphere is equal to 760 millimeter mercury column. Therefore, 1 atmosphere is 760 millimeter mercury. That's how you get millimeter mercury or torr. Measuring gas pressure, use a mercury manometer. When mercury is used for measuring pressure, it's called barometer. Manometer is a name, common name, used for measuring devices used for measuring pressure. There are a lot of gas wells in Louisiana. The gas comes with a certain pressure. You put the gas sample from the well into this bulb. The pressure of the gas sample that drawn from the well is obtained by this J tube. The pressure inside this vessel is equal to 60 millimeter mercury. Therefore, that's how we get different pressures of different samples by feeding the sample of gas into this bulb. This is a manometer. There are manometers used in different ways to measure the pressure. There are substances. There are crystals of substances. When you place them under pressure, they produce an electric current. So electric current is proportional to the pressure exerted on the crystalline material called piezoelectric crystals. Therefore, manometer made out of piezoelectric material could be calibrated to millimeter mercury. Therefore, we no longer use mercury manometers, but we use piezoelectric crystalline material with the same millimeter mercury calibration. Let's look at the questions about measurement of pressure. Which of the following instrument is used to measure atmospheric pressure? An altimeter. Is it one used for atmospheric pressure? Altimeter is used in airplanes to get the altitude. That's not the answer. Barometer is mercury manometer, using mercury barometer. We looked into that. Manometer is, we commonly use atmospheric barometer. Manometer is a general, all the instruments that used for measuring gaseous pressure. Thermometer is for temperature, is for not for. Therefore, only answer is barometer. What is the average pressure of atmosphere at sea level? On the average, if you take a barometer with the mercury column at the sea level, it normally shows up 760 millimeter mercury height. Therefore, 1 atmospheric pressure is equal to 760 millimeter mercury. That is just 1 atmosphere at the sea level. This is wrong. This is the B. This is wrong. That's not 7. It has to be 760. It's not 760 bars. Only 1 atmospheric pressure at the sea level is 760 millimeter mercury. Which of the following is the SI unit of pressure? I talked about it. SI units uses Pascal. So we gave the conversion factor in the previous slide. Answer is D. SI unit uses Pascal to measure pressure. Number 34. Which of the following is true of mercury level in both in the J tube? Remember, I look into J tube, you put the gas inlet into the bulb and measure the mercury height. If the mercury level at the same both sides, atmospheric pressure is equal to what is same pressure on both sides. So the gas pressure is higher than the atmosphere, lower than, that's not true, equal to the atmosphere. If you have a J tube like this, if the mercury level is same on both sides, therefore gas pressure is equal to atmospheric pressure. That's the correct answer. C. Let's look at some more problems. Which of the following units can be used to measure air pressure? Atmospheres. ATM, that's one of them. Millimeters mercury, that's one of them. Tau is one of them. Pascal is one of them. Bar is one of them. So all these three given are used for measuring pressure. Therefore, answer is D, all of these. Which of the following pressure relationship is correct? This is for psi 2. I didn't show you what psi is. Pounds per square inch is another unit for, that is equal to 762. Which of the following relationship is incorrect? This is correct. This is not correct. This is not correct. 1 atmosphere should be 14. It's 15 here. Therefore, it's incorrect. Correct answer is A. When you go to doctor, you get your blood pressure reading. You get 2 readings. Normally, people get 120 over 80, higher reading and lower reading, 120 over 80. The higher reading is for systolic pressure. That is the arterial blood pressure. Lower value is for blood pressure of veins. How do you convert this systolic pressure of 128 to 1 atmospheric pressure? 1 atmospheric pressure is 760 millimeter mercury. That's the conversion factor. To convert that, you start with the systolic pressure, and this is the conversion factor. You try to cancel the conversion units. That's the factor label method. That means systolic pressure, use the appropriate conversion factor, where millimeter mercury should cancel out to give ATM, you get 0.168. This is the correct answer. C is the correct answer. So this is similar to what you've done before. Use a conversion factor to convert one unit to the another pressure unit. There's another problem. Number 10. A scuba diver typically begins with a compressor tank with 2,350 psi. What is the pressure expressed in millimeter mercury? This is the conversion factor. Therefore, this is line up this value to cancel out psi. So I did the calculation here. You start with this to cancel the psi. You divide it by this conversion factor. Then left with millimeter mercury. When you do this number divided by these numbers, you get the 1.21 10 to the 5, this, which is the choice C. This is another factor label method, conversion, using the conversion factor for pressure, millimeter mercury to psi. Now we have different questions. Now psi converted to ATM. Just like the previous problem, you line up the psi, cancel the psi, get the 160 ATM, answer is A. There's another problem. How you convert 250 to Pascal. So again, you line up psi here to cancel out psi and end up with that's Pascal. Pascal 1.62. Answer is D. So you now gone over how to measure gas pressures and what kind of units are used in the measuring gas pressure, how to convert one unit to another. Now we are going to look at behavior of gases. We mainly deal with 4 variables. Volume, pressure, there's nothing in it. Volume, pressure, temperature, and number of moles of 4 variables. Now remember, for gases, temperature is in Kelvin. You cannot use Celsius or Fahrenheit temperature for gas behavior. Gas behavior, gas laws are using Kelvin temperature. How do you convert Celsius to Kelvin? You add 273 to Kelvin, Celsius, then get the Kelvin. There are various combination of variables. Out of these 4 variables, V, P, T, and N, you hold the V, T and N, Kelvin temperature and the number of moles. Fixed mass means N is held constant. N is constant. Constant temperature is temperature is constant. Therefore, you look at volume and pressure. How does the volume get affected by changes in pressure? Now, the Boyle's law says volume of a gas is inversely proportional to pressure. This is the proportionality. This is inverse relationship. Now, this proportionality N1 right here is always replaced with this equal sign nk. Therefore, you get PV is equal to constant. To remove the constant k, this is constant, you have to have two readings. If you know pressure of a gas and volume of a gas and change the pressure to P2 and get a new volume V2, you can make them equal and get rid of the K. Therefore, Boyle's law also explained in terms of this final equation. P1 V1 is equal to P2 times V2. That's the Boyle's law. Once you know these three variables, P1, V1, P2, you can rearrange the V2 and calculate V2. I'm rearranging it. Knowing that these three values, P1, V1, P2, you can calculate the V2. Once you know three of the variables, either combination, you can calculate the fourth variable using the Boyle's law relationship. Charles' law is dealing with volume and temperature, where the N and pressure is held constant. Volume of a gas is directly, this is direct proportionality. This is indirect, Boyle's law. So indirect relationship gives V1 divided by V divided by T is a constant. This is the proportionality sign replaced by constant. Therefore, we get a Charles law equation. V1 divided by T1 is equal to V2 divided by T2. Similar to Boyle's law, if you know volume of a gas, temperature of the gas, change the volume of the gas, and what is the new temperature. You can plug in the volume in liters, temperature in Kelvin, and get the final temperature, this T2 in Kelvin. So knowing three variables, fourth unknown variable could be calculated. Which of the following, there are problems now. Which of the following law relates the volume and the pressure? When the volume and the pressure, that's the V, P, amount is N, and Kelvin temperature is kept constant. That's the Boyle's law. Which is the Boyle's law? Out of these four laws, this is called inversely proportional to pressure of the gas. That's Boyle's law. And you got this equation. That's the correct answer to go for. If you change the volume and number of moles, that's Avogadro's law. If you change the volume and temperature, that's a direct relationship. Volume is directly proportional with temperature. That's called Charles' law. When you deal with pressure and temperature, holding amount, N and V constant, that's called the Gay-Lussac law. We talked about briefly, for a gas mixture, total pressure of the mixture is equal to sum of the partials. For example, for atmospheric pressure, mainly partial pressure of oxygen and nitrogen. If you know the partial pressure of oxygen in atmosphere, that's proportional to number of percentages. 20% oxygen, 80% nitrogen. Therefore, total pressure is 100. If the total pressure is 100, 20% come from oxygen, 80% come from nitrogen, adds up to this is ATM if you use ATM. That's for this question, Boyle's law is B. Indirect proportionality between V and P. At constant temperature, volume of a gas sample is 6. That's V1. And the gas pressure is increasing, that's P1 to P2. You change. Now they're asking, what is the new volume? V2. So this is a Boyle's law. Therefore, it deals with volume of the sample and the pressure. So you write down the Boyle's law. I wrote it down here. And solve for V2. When you rearrange this equation, you get the V2 is equal to P1 V1 divided by P2. V1 is 6 right here. That's V1. P1 is 1. That's P1. P2 is 2 here. When you do the calculation, you get new volume is 3.30 liters. That's how you calculate using Boyle's law. At constant pressure, the temperature of a gas is 56. Calculate the temperature of the temperature if the volume is gas change to 5 liters. That's the Charles law, similar to the previous calculation. You need to convert this to Kelvin. I have converted that to Kelvin. How do you convert it to Kelvin? Kelvin is 56 plus 273. That's going to be 300. 9, 7 plus 12. 50, I get the answer right here. When you do the calculation. I have more examples. That's the Charles law calculation. Volume versus Kelvin temperature. You look into the data at constant pressure and temperature. That's V1. Increase question is V2. I solve for V2, knowing that V1 is 4, right here, V1. Kelvin temperature, that's T1, T2. T2 is 400, T1 is 300. So we can calculate the final volume, which is D. Now, if you look at these questions, it's pretty simple to calculate unknown value of a variable from the given data, either Charles law or Boyle's law or Charles law. Similar calculation. Calculate the new volume. You get the same equation, same type of calculation. Now the question is different. You get 3 liters. I'm not going to go through each one of them. This is charge law calculation. That's how you get Kelvin temperature. This is the Kelvin temperature. You plug in the equation. New volume is V2. You solve for V2 right here and plug in the values of temperature and the initial volume, 4 liters. You get the final volume. C is the correct answer. Now, you need to go through problems yourself and see how you do the calculation. Gay-Lussac law is the third law. When the pressure and temperature, Kelvin temperature, is looked upon, while the volume and number of moles is held constant, you get similar to Charles law. Charles law is V1 divided by T1 is equal to V2 divided by T2. Gay-Lussac law is pressure in place of volume. So Gay-Lussac law is similar to Charles law, direct proportionality of pressure versus Kelvin temperature. You can do calculations just like you've done for Charles law. In summary, we talked about 3 laws. Boyle's law, P1 V1 is equal to P2 V2. Amount of substance and temperature held constant. Charles law deals with V1 divided by T1 is equal to V2 divided by T2. Pressure and amount of substance N is held constant. Gay-Lussac's law is P1 divided by T1 is equal to P2 divided by T2. Volume and the number of moles. Number of moles in each case is held constant. Now we try to get a combined gas law, combining Boyle's law, Charles law, Gay-Lussac law. Let's look at the first, before getting the combined gas law, let's look at Gay-Lussac law. Gay-Lussac's law is P1 divided by, this is the Gay-Lussac law. This is not. This is something to do with volume. Volume is not Gay-Lussac law. These are not the equation describing Gay-Lussac. This is the only correct form of the Gay-Lussac law equation. P1 divided by T1, P2 divided by T2. Now, which of the following laws? Number 32. The pressure and the temperature of a gas when volume is held constant. Volume and the amount is held. Relate pressure and temperature, Kelvin temperature. All the temperatures for gases are given in, must be in Kelvin. So this is the Gay-Lussac's law. Pressure is directly proportional to the Kelvin temperature. You get this equation. Therefore, answer is D, Gay-Lussac law. This is, pressure is directly proportional to Kelvin temperature, while fixed amount of gas and volume is held constant. This is the Gay-Lussac's law. P1 divided by T1 is equal to P2 divided by T2. As I try to explain, three gas laws could be combined into one gas law called combined gas law. Boyle's law, Charles' law, Gay-Lussac law can be combined into combined gas law. Now you have a combined gas law. If you held temperature constant and the amount of substance N is constant, it goes to Boyle's law. You can look at if the volume is held constant, V1 is V2 cancel out. Held constant means same value. Then it becomes Gay-Lussac's law. If you held pressure constant, then it goes to Charles' law. Therefore, combined law summarizes the whole idea about three gas laws: Boyle's law, Charles' law, and Gay-Lussac's law. If you do a problem like this, gas has V1, P1, that's the pressure. Calculate the volume, that's the P2. Volume, new volume, that's the question. Now, this will be combined gas law, where the pressure is held constant, temperature is held constant. Therefore, T1 is equal to T2. So these cancel out. Or you can rearrange the V2. Here, V2 is the question. T1, T2 cancel out. End up with Boyle's law calculation. So combined law eventually gives same result as one of the gas laws. Which of the following is identical representation of the combined gas law? If you look at the combined gas law, this is the only correct answer. This is the mathematically equivalent. If you put them below T2, this one below T1 is same as combined gas law. All other mathematical relationships doesn't give identical expression to combined gas law. So therefore, answer is C. C is the mathematical representation correct for the combined gas law. Suppose a balloon is filled with 2 liters and the pressure is 362 and the temperature is 24. You need to convert it to Kelvin. They are asking what is the volume. They are asking V2. That's a combined gas law. They are asking V2. So the V2 is this Charles law, combined gas law. It solves for V2. So you can plug in the values of known values of temperature in Kelvin. Then you can plug in the values, do the calculation. You get 4 liters, which is the D here. So that's how you do calculation with combined gas law. Gas law that relate to pressure, volume, temperature. Number 76. Select the mathematical expression for gas law listed. That's same as combined gas law. D is the correct answer. Are you guys there? I'm going to talk about Avogadro's law. Avogadro's law is when the variables are volume and the amount of gas, moles, amount of gas, temperature and pressure held constant. From Avogadro's law, you can say equal volumes of a gas at same pressure, same temperature and same pressure have same number of molecules or moles. Avogadro's law is direct proportional. Volume of a gas is directly proportional to number of moles. When you replace the proportionality with the constant and get 2 readings, V1 divided by N1, V2 divided by N2 are equal. That is the statement of Avogadro's law. The actual temperature doesn't matter. But when you are comparing 2 gases to certain temperature or pressure, we use standard temperature and standard pressure and temperature. It's called STP. STP is 0 degrees Celsius, 1 atmospheric pressure, or equivalent form. It could be 762 and 273 Kelvin. 0 degrees Celsius is same as 273 Kelvin. The carbon dioxide sample, 1 mole of carbon dioxide sample has 22.4 liters at standard temperature. Which of the following statement is true of the sample? Carbon dioxide contains 1 mole of carbon dioxide. If sample has 1 mole, it always has 22.4 at STP. That's the 1 mole of carbon dioxide. 1 mole of carbon dioxide has Avogadro number of carbon atom. That is true statement. The sample contains twice this number, Avogadro's number. Therefore, it's not true. The sample contains less molecules of carbon dioxide. That's true. The true statements are A and C. I gave only C. A is also correct here. Most obvious answer is C. That's why I picked that up. Avogadro's law gives us volume of a sample, 1 mole of sample. 1 mole of sample at standard temperature and pressure has a 22.4 liters. I'm going to show that calculation little later. What volume does 1 mole of oxygen gas occupy at the temperature? That is the ST 273 or 0 degree Celsius or 762 are the standard temperature and pressure. So 1 mole contains 6.02 to 10 to the 23 particles or oxygen molecules. So one mole of oxygen should be at STP is 22.4 liters. Therefore, standard temperature and pressure is important for comparing volume of gases, different amount of gases. One mole of any gas at standard temperature has 22.4 liters. This comes out of Avogadro's law, where volume is directly proportional to number of moles. I'm going to stop the class for today. You guys go back and do some problems in chapter 5. Okay, you guys are here. I will see you on Thursday. Did I lose you guys? Anybody there?
Yes, sir.
I will see you on Thursday. Okay?
Okay, you have a good one.
Yeah, you too. Bye-bye.